first presentation after lunch is provided by Ove Bratland, who is an independent consultant in the field of flow assurance. And he has a lot of experience in all different related fields within flow assurance, and he's going to give a presentation about flow assurance simulators.
Thank you. Dr. Ruud Henkes has already enlightened us a lot now about what flow assurance is all about. So I will try to continue a little bit from there. About what the current status is, what can we do with flow assurance and what can't we really do so very well. And what about the future? Will it develop into something where you just click a button on a program and then we get all the answers, or is that unlikely to happen? The flow assurance definition, there are lots of them out there. This is a term which has been around only for 20 years or so. So it's a relatively new discipline. It is about ensuring that the fluid flows as intended through pipes and wells from inlet to outlet. So it's all about not getting problems in our flow lines, or wherever we define our inlet and outlet. It can be far down in the well, for instance, we define as inlet, and outlet can be the outlet of our flow line, or it can in principle include the whole process plant if you want to include that in your definition. So flow assurance in practice often comes down to a first point I have included here, which is a little bit untraditional, I think, to include in flow assurance, and that is having sufficient capacity in your original design. Even in single-phase flow, as we will see, the friction calculations aren't always as accurate as we think they are, and we can end up with a too small or too large flow line. In multi-phase flow, friction is much more complicated, and there's even bigger chance of ending up with not having the capacity we would want. Also, avoiding pressure surge problems we have heard about. Both fluids, they focus on that. How do we avoid high pressures that can damage our system? That is mostly a problem in single-phase liquid flow. It's not so much of a problem in multi-phase flow, believe it or not. You might think when you have slugs and everything moving around there, then it would create big pressures and maybe destroy our pipes. But that's not the main problem because it's relatively soft. You have many bubbles in there also, so it's not so hard pressures, you might say, coming out of it. And then it's about keeping the temperature high enough, maybe to avoid hydrates. That's one possible strategy. Or low pressures are also a good thing when we want to avoid those types of problems. Maybe we add chemicals, we add mag or something in order to avoid hydrates building up. It could be we use pigging, as we saw here, as a strategy for getting out liquids that build up in our flow line, or to get out wax. Managing slugging or avoiding slugging altogether if we can, that can be a big part of our problems. Erosion and corrosion can be. We mostly talk about what's going on inside the pipeline when we use the word flow assurance, even though corrosion, of course, is a problem at the outside also, but it tends to be a different group of people who focus on that part. We may have to cope with emulsions and gelling. Oil and water, for instance, can mix in a way that makes the viscosity very high, and we can get gelling. It is kind of gel forming in there which doesn't want to flow at all. All of these things we may have to deal with when we do flow assurance. As an example, for hydrates, some of the strategies we may apply, we may try to remove the water, then we tend not to get so much hydrates problems. We can keep it hot, keep the temperature higher than where hydrates start to form, or we can keep the pressure lower than where hydrates start to form, or we can inject a lot of inhibitors of the traditional sort, or, as we heard before today, you have other more clever ones where you don't need so large amounts of them, but where they don't work permanently. You have to hurry up and get your stuff through the line before these genetic ones stop working properly. We have also seen other exciting developments. For instance, cold flow for hydrates. There's been a lot of research work on that. Can we transport hydrates in the flow line? Instead of stopping it from forming, we allow it to form, and then we transport the whole thing. It has been difficult to do so. It's been spent quite a lot of money on finding ways to do it. Then you could avoid many of the chemicals or the heating or the other things you need to do in order to avoid problems. I don't think we can say cold hybrid flow is a mature thing at the moment, but that may be a way that will become common in the future. One thing that is not being done normally in calculation of potential hydrate problems nowadays, you do not take into account the heat generated by the hydrate itself. The most traditional way is to make sure our temperature doesn't fall down to the temperature where we get hydrates. Now, it just so happens that when we come down to that temperature and hydrates start to form, then the hydrate formation itself releases energy. Almost like when water freezes on a lake. Once we're down to 0 degrees Celsius, we start to form ice, but the temperature doesn't continue to fall. We just get thicker ice. And some of the same things happen with hydrates. So in more accurate calculations, we could take that into account. That's not built into the standard software as they look today. Now, here is one of the fundamental challenges we have in flow assurance. And that is, when we want to model how fluid flows, much of the action to do with friction, which is a very important factor. Friction is what determines the capacity we get, and also determines how well we manage to drag liquid out of a flow line by injecting gas through it. The action in friction is on a very, very minute scale. When you form turbulent eddies in a pipeline, they break down and become smaller and smaller and smaller. And the final friction contribution, if you like, happens when they have become very, very small, like microns, very, very tiny. So tiny, in fact, that if we want to simulate it directly, we would have to have a very, very fine grid, so fine that we can't do it. So therefore, with all the fancy 3D simulations and everything we have nowadays, nobody has come up with anything more accurate by simulating 3D than measurements which are 70 years old, which gives us a factor that we multiply with something in 1D. So its empirical calculations are still more accurate than the 3D calculations. So that shows us that there are limits to what we can do, although 3D calculations, of course, can be very useful for many things. But they are not easy to use for everything. This diagram I have included just to show you that we engineers, we have been a little bit slow actually at adopting known knowledge in calculating frictions in single-phase pipe flow. This is Nicaratz's diagram. He is a German who, nearly 70 years ago did a lot of measurements of what friction is like in single-phase flow. And he found out the diagram that looks a bit like this. I just extended it a bit, so this isn't his original diagram, but it basically is shaped in the same way as what Nicaratz found out. And one of the things he found out is that when our friction factor, Darcy-Weisbach friction factor, for certain Reynolds number is lower. This is the Reynolds number along here. And you have friction factor along here, and then you have various roughnesses depending on how rough your surface for your pipeline is along these lines. So they go down here, and also there is no jump when you have turbulent flow, which you have over here, and if you reduce your Reynolds numbers until it becomes laminar, it's actually a continuous line. He measured that, and other measurements later have confirmed that. But the diagram engineers have used for 30 years doesn't look like that. It looks like this. No compare, huh? Does it look the same? No. So what we have done is we have said, okay, we use the same as Nicaratz out here. And then we just think Nicaratz, he was plainly wrong up here, so we do something completely different. And then we curve these in a very different way than any measurements have ever shown. So that means if we design a pipeline, even single phase, and we happen to be at Reynolds numbers and relative roughnesses, which happen to be in this particular area here, we are plainly very inaccurate in our predictions, even for single phase flow. It can be 10% wrong, can be even up towards 15% wrong, maybe, the friction factor. And in this area, we are way off if we follow these predictions here. I don't know how this came about. Well, actually, I know. They said, okay, this is right, and this line is right, and then we just make a nice smooth curve in between. That's probably also right, but it isn't. Now, once we go over to multi-phase flow, of course, the frictions become even more difficult. So here are, again, some of the problems we are up against. Kolmogorow's length scale is very small. He was that Russian who understood more about turbulence than most other people. Nobody understands very much about it, but he understood as much as possible at the time, at least. Turbulence is very, very complicated, at the minute scale especially. And he came up with how small these things are, which really matters in the flow. When in real flow lines, we have 3D phenomena varying over time, so in a way it's 4D. That's what they are. But the simulators used to simulate whole flow lines, they can only do things in 1D. They are not capable of doing it in 3D, and as we have done, even if they could, they are unlikely to come up with better friction calculations, because that we can't even do in 1D better. So there are some problems. And then we have problems with numerical mathematics. We like to think that the mathematicians, they found out everything a few hundred years ago, didn't they? No, in fact, they did not. Those who are developed numerical mathematics, they are still amongst us, walking around and trying to improve their models. So that's relatively new. So the equations we have to solve, and we typically solve in 1D in Olga and in Leda flow, they are so-called hyperbolic equations. And the way to solve them, there are no very, very good ways to solve them, believe it or not. So you still have a lot of papers coming out. We should rather solve it like this. No, let's do it like that. And maybe my equations won't be properly hyperbolic if I do it wrong and we get the wrong answers. So even on the mathematical side, there are challenges. We see that those mathematicians, they are very capable, so it looks like they are getting better and better at giving us methods that work well. So we can expect further progress there, I think, into the future. Then there are many chemistry challenges we are faced with when we are trying to do flow assurance in flow lines. We need to know the composition. We need to know what we have, basically. What kind of oil, what kind of gas do we have? And that can be difficult to take representative oil samples so that we know what we have. And once we have those accurate samples, it's then next difficulty is to extract from those samples what my actual properties are. You have chemical programs that help us with it, but they are also only mere mortals, just like the rest of us. So it's not perfect what comes out of that. The mechanisms involved in hydrate formation, waxing, corrosion, diffusion, and others are rather complicated. And we can't just go to the chemists and ask them and they will give us the whole answer, because it just so happens that how this forms in the flow line also depends on pressure, temperature, and Reynolds number. So the chemist can't solve it alone, and we, on the fluid mechanical side of things, we can't do it either. We have to cooperate, obviously. Then when it comes to programming, there we have seen many exciting developments on the software side, because programming languages, they develop, and Moore's law is ticking along, but we have also all these parallel processors nowadays, and we can rent even a one-man company nowadays can rent in the cloud a lot of CPUs, a lot of cores. So if it's possible to use those cores in a sensible way, that's a big if. But if you can do that, you can have access to it. You can rent the cloud from Microsoft or from whoever. There are many of them nowadays. And also so I think that will open new possibilities. Up until now it has been universities. Even when I was a student, which is by now 30 years ago, we had these supercomputers with parallel processing and all that, so it's been around for a long time. But what is so new about it is that it has become so available to absolutely everybody. And then I think it takes time before this same everybody has time to adapt it to their application. And I think it also opens potentially new possibilities for business models. Maybe I know that Olga and Dynaflow, they do not put their stuff in the cloud, so we can just rent for an hour or something and do our simulations. They don't do it now, but who knows what somebody will do 10 years from now. I think we will see new business models based on cloud-based services, and we haven't had time, any of us, to think through how that should be done properly yet, but it's likely to have an implication, I think. So we don't know how to utilize it. Parallelization is a challenge in itself, how to parallelize in such a way that it becomes efficient. I mean, you can probably rent 100,000 cores for a minute if you want, but can you really make them do anything useful for you during that minute? That's a completely different question, and it typically requires a total reorganization of your software for that to be possible. And I think there are also security issues. Will a big oil company of not spoken name here right now, would they really deposit a lot of data into a cloud if you had a cloud service where they cannot control it? Maybe not. But the cloud can be also in their own location. So there are also things that will come into this, I think, in the future. So how do we choose software then? There's a lot to choose from, isn't it? If you do flow assurance, we just grab one and then we simulate, and then out comes the answers. Well, no, not really. Because if we have three-phase flow, and that just happens to be what we often have in flow lines, and we want to simulate what happens from over time, we want a transient simulator, then there aren't so many. Commercially available, it comes down to this one and this one. The other ones are nice in their own ways, but they aren't transient multi-phase simulators. So we may want to classify the different tools then like this. They are single-phase or multi-phase. Or they may, to some extent, be multi-phase, but not fully. For instance, both fluids can simulate single phase, and they can also go into cavitation, which is kind of a multi-phase thing. But full multi-phase simulators, that's Olga and Dynaflow, or the commercially available ones. And they can be only steady state, or they can be transient. There are several other steady state ones, but the transient ones are considered more advanced. They give you more information, they are likely to be more accurate, and they are likely to be more expensive. Now, all of the simulators, they have more or less these things, at least the multi-phase ones. They have a steady state part built into them, and they have a transient part also. Olga and Dynaflow, at least. They have various levels of thermodynamical simulations. You simulate how it loses heat to an environment. And that can be steady state or transient also. Even if the hydraulical part is transient, then the thermodynamical part doesn't have to be fully transient. So there are many levels of how transient it can simulate, if you like. It has to determine which flow regime they have, And that's what they are least good at, I think. It's difficult to do that accurately. Do you have slugs or not? Do you have stratified flow? What do you have in there? How does it flow in there? And they also handle PVT properties differently. They talk to three-party software, at least that's what Olga does, and takes chemical properties from another software package. And they can have various graphical user interfaces also. So here are some of the flow regimes they have to deal with. They have to deal with annular flow, dispersed flow, stratified flow. Maybe they deal with churn flow, horizontal or vertical slugs. So that looks like quite a chaos. But the reality, which they don't talk so much about, is even more chaotic, much more so. For instance, if you look at two-phase liquid-liquid flow, the amount of combinations that actually do exist in real flow, there are many more combinations than any simulation software talk about, simply because they have to simplify to make it more or less manageable. But then at the same time we have to accept, okay, then it won't be 100% accurate, of course not, because we have kind of ignored some of the potential ways in which the flow can exist inside our lines. In three-phase flow, of course, it's more complicated yet, because we have can have oil, let's say, and gas and water. And modeling that accurately is more difficult than two-phase flow. But it just so happens that three-phase flow is what we have, whether we like it or not. The number of combinations of flow regimes that can lead to when you have liquid, and gas mixing in all sorts of ways, it's so ridiculously many that I haven't even tried to illustrate it in this diagram. So we can have, for instance, if we have only gas and oil, then we have flow regimes, for instance, of the type on the border here, or gas and water. We may have flow regimes like this, or we can have many, many more, by the way, if we have oil and water. So that's if we have two-phase flow, basically. Three-phase flow, we don't even try to fill in what all the combinations that may look like. And neither do Olga or Leda flow, because that's just too complicated. So we can have the software we use in practice can be single phase, or it can be steady state or transient. It can be for liquid or gas if it is single phase. And it can be general software, it can be specialized. For instance, some specialize on gas networks, and there's certain niches there. For studies, they can be steady state or they can be multi-phase. Once we go into multi-phase, there are far fewer to choose from, because we go into a much more complicated problem area. And the general ones for long lines, the transient ones, there are very few. There are other things we can do with them, but let's not go too deep into that. So here are some of them. There are many others who have tried to enter the market and who have partly done so for a short time, but it has turned out to be difficult to compete with Olga, which has been the dominating one for 30 years. Dynaflow is the new kid on the block, which is then owned by Kongsberg. Schlumberger have taken over SPT Group, which is the owner of Olga. And these, I think, has more or less given up. That has been difficult. But also, it's worth mentioning, there are many software or pieces of software, if you like, around at universities around the world, and also some oil companies have things they have done in-house. So this isn't the full story, but these are the ones which are commercially available. When it comes to these limitations we are faced with, meteorology is a very scientific field, and we have a lot of very clever people there who are working all the time, and they are improving their models. They have finer mesh in their 3D models and all that, so they tell us more and more about the weather. But they still cannot tell us what the weather is going to be 1 month from now. And that's not because they're not clever, and it's not because they have done errors in their programs or anything. It's simply because the nature of such a question is so complex and complicated that it's not within the grasp of any near future to answer that. And I think this is somewhat similar to what we will see in flow assurance. We can definitely improve a lot compared to where we are now. But there are limits as to how far it's realistic for us to come. It's a little bit like with the weather. We can't go anywhere. We can't predict all sorts of situations. It's plainly too complicated, too complex for that. So if we should summarize the current situation, I would say that single phase is quite mature, but believe it or not, friction, which has been around for a very long time, isn't really mature. We still model things in a relatively inaccurate way with those strange curves, which do not agree with measurements very well. It comes down to a fundamental problem that the friction diagrams try to model roughness of a surface by simply modeling how high the roughness is, the distance between peaks and valleys of roughness on a pipe. And that isn't a good enough way to describe a surface. A surface has many types of roughnesses at the same time, and the distribution of different types of roughnesses plays a role. And no pipe manufacturer tells you that. They tell you what the internal roughness is. And that's not enough. You need more information than that to know the shape of your friction curve properly. So apart from that problem, single phase is quite mature. Several multi-phase steady-state simulation programs exist. Only 2 commercial multi-phase transient full-phase flow assurance programs exist, Ove and Dynaflow. We actually have also seen an owner concentration. Numerical hasn't only bought Olga or SPT Group, they have also bought a lot of the steady-state simulation software. So they now own very many. That's probably a nice thing to own very many, especially for those who own them. But that means we have an owner concentration more than we had before. A lot of research is ongoing. I've gone through many of these research papers that come out all the time, and it's very interesting. You see in fluid mechanics, there are lots of PhD around the world that do great jobs. We have also in chemistry, there are people who work hard there, in corrosion control, in mathematics also. So it's a lot of people who do things here. But it is still the situation that we don't know enough, plainly, to do as good model as we would want to. In the future, the flow assurance market is expanding. I think that's fair to say. There are more things we can do with the flow assurance than before, and in the North Sea, there are all the old platforms. They build out new things around them all the time nowadays, and you want to transport multi-phase maybe back to the nearest platform. You don't build a new platform on top of anything, so you get more multi-phase. Now it's believed that most of the simulations are done with steady-state software, but there's probably going to be more of that will happen on the transient simulators because they are more accurate. New knowledge will continue to appear very fast, and much more knowledge exists already than has been implemented in any simulator. 1,000 papers or more relevant to flow assurance comes out every year. There's nobody has the resources to extract all the information that's in there and implement it in any simulation program. So therefore, there is kind of a lag, I think. Some of the information that comes out from all the research which is done is hard to utilize in practice because it isn't always part of the simulator at all. And it ends up in a drawer, at least for a while. So that's one of the challenges we have, is to utilize all the research well enough. None of the software tools are good enough. Of course, they never will be good enough, but I think we still will see improvements there. We will see more of integration between Olga and Eclipse. Of course, there's a well simulator which now is owned by the same company, so they will probably work hard to make you use both of them together. There are physical limits like length scale in the weather forecasting sense that you never get to that 1 month, no matter how long you do it. More training and education in flow assurance is necessary, I think, and it's also expected. It hasn't been something that was identified as a word or well, flow. Some of the things done in multi-phase flow is the same, I think, as what I think about when I call it flow assurance. I teach myself part-time intensive courses in Singapore, National University of Singapore, and they also have in Houston, in Norway, here in Delft. There is also students being trained, and I think that's a great idea because using the simulation software which is out there is so complicated. You cannot use it as a black box. You basically have to know what you're doing, no less. You have to evaluate what comes out of it. And that means you need to have knowledge. Open questions: how much 2D and 3D do we put into those simulators? We simulate complete flow lines. I don't know the answer to that. I suspect we will go a little bit in this direction, but as I said, there are limits to what we can achieve, especially in friction. How many software systems will there be? Now we have Olga and Dynaflow. What about the new cloud-based business models? Will they emerge? Will they be used to get higher computing capacity? Will we see a faster research progress due to the very cheap parallel processing power which now becomes available? And also here's an outsider. You know, we know that in the US they have now found so much shale gas and partly oil that they are now almost have enough gas for themselves. Nobody would predict that, had predicted that 5 years ago. So the Stockman development, which was supposed to give gas to the US, and all the engineers have done a lot of technical work and everything looks promising, then the customer is gone. So then maybe no Stockman. So, so the new market situation here also is a factor that comes into it. Okay.